start to introduce Professor Scheeres from University of Colorado, Boulder, and I think no need. He will present his lecture with the title "The Geophysical Environment of Asteroids, Bennu and Ryugu."
Yes, that's right.
Yes, you know the time.
Yes. Thank you very much, Yuri, for the introduction, and thank you for being here. I'm going to talk a little bit about two asteroids that are currently being explored by two different spacecraft. One of these is the asteroid Bennu, being explored by the Asuras Rex spacecraft. The other one is the asteroid Ryugu, being explored by the Hayabusa 2 spacecraft team. I'm fortunate in that I'm a co-eye on both Asuras Rex and Hayabusa 2, so I've been able to be very much engaged with some of the different activities associated with both of these exciting missions. First of all, the material I'm going to show today, especially the second half, I have a brief intro to the two missions first, is taken from a series of different publications that have just come out this year. Some about Hayabusa 2 at Ryugu, Watanabe et al. And Suguta et al. In the journal Science, and then a series of papers put out from the Asuras Rex team about the asteroid Bennu, led by Dante Loretta's paper in Nature, and then a series of other supporting papers, plus several more that aren't relevant for the talk here, at different Nature publications. So first I'm going to give you some basics about these two missions, Hayabusa 2 and Asuras Rex. The Hayabusa 2 mission, and I think it looks probably better on the screens there. So, oh yeah, if we could turn the lights off, that would probably be appropriate as well. So anyway, the Hayabusa 2 mission is a sample return that goes to the primitive asteroid Ryugu. And it launched a few years ago. Right now it's currently in the middle of its activities there, and it's scheduled to complete its activities and head back at the end of this year or beginning of next year. They've taken a particular approach to their close proximity dynamics, which is interesting to a crowd like this, where they've actually implemented a hovering regime where they basically have boxes, control boxes, deadband boxes that they set up for the spacecraft, and they allow the spacecraft to come down to the surface. When they get very close and touch the surface, they actually go autonomous, but other than that, it's all sort of ground in the loop for the control of this satellite, and it's been quite successful, actually. Here are a few highlight images from the mission. This is Ryugu, which is in fact a very rocky asteroid. These are a still image in a movie actually taken from the surface of the asteroid by some of the small rovers that were deployed to the surface of the asteroid. It was last October even that this was performed. And they've done a series of these descents to the surface and back up again, deploying target markers and the like, all leading up to a successful sampling that they undertook in February of this year. And this picture taken on the spacecraft is pretty amazing, this movie. You see it coming down, touching the surface, it takes a sample, and then it blows its thruster system to back off from the surface, and that effect sort of raises up this whole cloud of rocky material scattered around, chasing the spacecraft up as it went back up into its hovering location. So this is the before picture of the sampling site. This is the after picture where you actually see that they disturb regions of the surface. And this is, in fact, it was hard to see, but this is the actual spot It corresponds to where they took the sample. Since then, in fact, they've had another great success, which was to deploy a cratering experiment that actually created a 10 to 20 meter crater on the surface. It's a part of a complex endeavor that involved two smaller satellites that they carried on board. They jettisoned. One of them actually shot a penetrator into the surface. Here we see a very fuzzy image from the second deployed camera showing a small ejecta field, implying that they certainly hit it. And then before and after pictures of the cratering site also shows that they've made a crater. And then here you actually see where they just dropped the target marker for their navigation to go and collect some samples from the regime around this cratering experiment. And that's going to happen in the next week or two. So they're very active. They're going through a lot of very exciting activities. The other mission I'll talk that the data is based on is the Asuras Rex Mission. This is also an asteroid sample return mission going to an asteroid of a very similar type. And actually Hayabusa 2 and Asuras Rex are independent of each other, but they have agreements that they will share the material that they sample with each other. So what is Asuras Rex? It's a sample return mission. It will return at least 60 grams and as much as 2 kilograms of pristine carbonaceous regolith from the asteroid Bennu. It's currently at Bennu. It launched a few years ago. We rendezvoused late last year. We'll be sampling mid next year, and we return to Earth in 2023. It's a NASA mission, so its name is also an acronym to study origin, spectral interpretation, resource identification, security, and to explore the regolith or the surface covering on an asteroid. This is the rough size of Bennu, and we'll actually do some comparisons between Bennu and Ryugu in just a little bit. About 500 meters across, a spheroidal spinning top, spinning relatively fast at about 4.3 hours. When we study Bennu, and the reason why we want to study Bennu is that we study the material that the solar system was actually formed out of. And this is true for both Hayabusa 2 and Asuras Rex, and this is what mainly motivates them. But once we're in proximity to these bodies, we actually get a lot of very interesting information as well that really furthers asteroid science. One interesting fact about Bennu is that it's actually the most potentially hazardous asteroid that we know of. It's not hazardous now, but its orbit evolves, and it will intersect the Earth's orbit in about 150 years from now. And at that time, in like 2182, impact odds are about 1 in 1,800, based on our current measurements. So that's a fairly high probability of impact, which also makes it interesting to study this body just in case we need to deflect it. And by the end of the mission, we'll have a much better sense of what the impact odds are, or whether in fact it will definitely miss us. We don't have those numbers yet. So once we go to once Asuras Rex goes to Bennu, we carried out a series of activities, taking reconnaissance images, mapping the surface in detail, measuring Bennu's mass and gravity field, shape and spin state. Right now we're in the process of choosing our touch and go site. That will start to characterize those sites and will culminate next year in an actual sampling of the surface. Spacecraft are operated at close to us in Denver at the Lockheed Martin campus. And right now it's actually in what we call a Terminator orbit, which is a special orbit that actually balances solar radiation pressure and gravitational perturbations of the asteroid, and actually naturally tracks the sun, not because of oblateness, but because of solar radiation pressure. Okay, here's a couple of nice images. Again, this is an extremely rocky body, very difficult for sampling the surface. Here's, maybe these show up better on the screens there, but a couple of close-ups of the environment on the surface of this body. Here's a larger picture, 2 detailed pictures, and you just see how at every scale there's a lot of boulders, a lot of rocky material. It looks like you would cut your fingers if you touched the surface. One interesting aspect, which you can barely see here, is that the asteroid has also been spitting out particles from its surface, some of which actually go into orbit for about a week or so before they re-impact. That's also unprecedented and completely unexpected. And it's very exciting, and in fact that gives us a very good opportunity to measure the higher moments of the gravity field, in fact. And then this is an interesting sort of a stereo picture. If you cross your eyes and look at this, you'll see the rock pop out, but don't do it now, because I'll show this again if we're ready. Okay, so now we've gone to these 2, in some ways, very similar types of asteroids. It just makes sense at this stage to do sort of a side-by-side comparison of the 2 of them. Because when you look at them, they actually seem to be quite similar. These are slightly different resolutions, but the surface of Ryugu is about as rocky as the surface of Bennu. They both have sort of this characteristic oblate shape, and so it just makes sense to do some direct comparisons of the environments at each of these bodies. So we can go through and actually point out a number of similarities and differences between them. First is that the size of them is in fact different almost by a factor of 2. Okay, the mean radius of Ryugu is about 450 meters. The mean radius of Bennu is about 250 meters. Because of this, the gravitational parameters are different by about a factor of 5, actually 6. However, when we actually take the volumes and divide by the mass, we find out that to our level of precision, they actually have exactly the same density. And based on this density and based on the material, we also believe that each of these asteroids is about 50% porous. That means that 50% of the material inside of this asteroid is actually empty void space. So that's a very porous asteroid, and actually quite interesting. Has a lot of implications for how they form and actually how they evolve. The spin periods are actually different, not quite by a factor of 2, but we'll see that this actually makes the major difference between the current environments about both of these bodies. But based on the measurements we have of Bennu, we also know that Bennu probably had a similar rotation period relatively recently. The heliocentric orbits of them are actually pretty similar, perihelion and aphelion, so that they lie roughly the same region of Earth's orbital space. And if we actually look at the constant density gravity parameters, and these are really the mass moments of the bodies, if we look at the oblateness, the ellipticity, the J3 and the J4, and these are all normalized, we find that they actually have remarkably similar values. And this is borne out when you look at the bodies and you see that the shapes actually seem pretty similar to each other. So, the first thing that we can notice, because they have the similar shape and the similar density and the similar heliocentric orbit, the relative orbital dynamics about each of these bodies is actually quite similar. The only difference is really due to the size. And here, when we are in orbit, we can pretty much ignore the C22 or the ellipticity of the equator and treat them as rotational spheroids. So if we take a given particle area to mass ratio or spacecraft area to mass ratio, we find that the maximum orbit radius about Ryugu is going to be about a factor of 1.35 larger than the maximum orbit about Bennu, just because Ryugu is larger. Another way of putting it, at 1 AU, the maximum orbit the spacecraft could have at Bennu is about 1.8 kilometers, or about 7 Bennu radii. That same spacecraft could have a maximum orbit radius of about 4.5 kilometers at Ryugu, or about 9 Ryugu radii. When we get close to the bodies, there is significant differences that we see, and I'll show you that in a second. But here are examples of some sun-synchronous Terminator orbits, again using solar radiation pressure to balance things. Asuras Rex is definitely using one of these orbits at Bennu. The Hayabusa 2 mission is not using these at Ryugu. However, for some other reasons, we've analyzed their stability of these. And you can sort of see the largest orbit is the outermost orbit here. You probably go a little bit larger, but then it would be stripped away. And the smallest orbit is roughly the smallest orbit that we see here. If you get closer, you get destabilized by the gravity field, and in fact, you impact again. So when we look at the dynamics closer to the bodies, then the shape starts to matter a lot. And what we find is that the dynamics are mainly driven by the one-to-one resonances with the body's rotation. And for Bennu, since it's spinning faster, that resonance point is much closer to the body, at about 1.25 radii. Ryugu, which is spinning slowly, the one-to-one radii or synchronous orbits are about 1.8, 1.9 radii away from the surface. So if we look at the two bodies, and here it's roughly in scale size, but I'll just blow up Bennu so we can see it a little bit better. We see, because of the non-rotationally symmetric profile, and here we're looking down on the rotation pole, that they have different numbers of equilibrium points. Ryugu has 6 equilibrium points, Bennu has 8 equilibrium points. If we spun Ryugu faster, it would actually gain additional equilibrium points. If we spun Bennu more slowly, it would actually lose some of these equilibrium points, eventually going to probably 4 at a very slow spin rate. Now, with these equilibrium points, we can actually study their hyperbolic manifolds and their center manifolds. And what we find at Ryugu is that all the center manifolds are in fact stable, and the hyperbolic manifolds really just form a ring of radii around the body. And if we propagate them out for a long time, you have some variation away from the body, but really the surface of Ryugu is really shielded in phase space from the stable and unstable manifolds of these equilibrium points. That means that material lofted at slow speeds on the surface of Ryugu will tend to stay trapped inside of this region and not interact with the synchronous orbits. Situation is completely different at Bennu. Here, of course, the hyperbolic orbits, and there are 4 of them, have the stable and unstable manifolds. And here's looking at the ones that actually come down to the surface. And we see that we can easily eject material and have it hang out by an equilibrium point in the stable sense, and then escape on the unstable and re-impact the surface. And we also find that right now at least 3 of these center manifolds are also highly unstable, hyperbolically unstable. And material can be lofted from the surface and actually hang out in the vicinity around these points for a while. Right now, it looks like there might be 1 equilibrium point that's stable, but its stability is very sensitive to details about the mass distribution. So because of this, we find that the synchronous dynamics for Bennu all interact very strongly with the surface, so material lofted from the surface is subject to a very strong chaotic motion. The accelerations, so given the orbital study, we can now look at the surface geophysical conditions at these bodies, and we'll look at accelerations, slopes, potential energy, return speeds, and escape speeds. Surface accelerations on Ryugu and Bennu have a similar pattern, lowest at the equator because of the rotation, highest at the poles. Ryugu's maximum is 150 micrometers per second squared. Bennu is 80 micrometers, and the minimum at Bennu is lower at 30. We can also look at potential energy speeds, and this is the speed that a body would, say a marble would gain if you took it to the highest point in the potential and let it roll downhill. For Bennu, we see that that downhill region is actually at the equator, and it would actually gain 10 centimeters per second, which at Bennu is enough to send it off into orbit. So you could actually roll downhill on Bennu and go off into orbit. Ryugu, which is larger, that lowest potential energy point is actually at the mid-latitudes because it's spinning more slowly. And by the time you get to the equator, you would actually slow down a bit again. Here, the speed is not fast enough to actually go into orbit. So again, Ryugu, if you have material rolling down its surface, is trapped. That material is still going to be trapped to the surface of Ryugu. We can also look at the surface slopes. This is if you stand on these bodies. This is the angle between the local total acceleration, spin acceleration, and gravitational, and the local normal. And again, we start seeing a difference where Ryugu has stronger slopes at the equator. Bennu has subdued slopes at the equator. Ryugu has subdued slopes at the mid-latitudes, where Bennu's is more intense. If we also plot what we call the return speed, and this is the speed below which you are guaranteed to be trapped to the surface, we see a big difference. And in fact, parts of the Bennu surface actually have a high enough energy so that you could actually roll down to the surface, go into orbit, and actually escape. You cannot do that on Ryugu, where all this material is linked. And what we actually see here is that where this thing that we call the Roche lobe intersects the surface actually corresponds to the change in slope on Bennu. So here we have, this is from our Nature paper, looking at the slope structure, also looking at that Roche lobe intersection on the surface, and then looking at some of the average slopes. And what we see is that inside of this essentially zero velocity curve, material is actually trapped. So any material that gets lifted up, like the particles that we saw, is actually going to be preferentially trapped inside of this region. And this is one explanation that we have for the lower slope in this region. This is sort of an interesting concept, but I think I'm running out of time, so I'm going to skip through this slide. It's many builds. This is part of the main scientific analysis, was to study aspects of this Roche lobe on Bennu. And then finally, we can also look at the escape speeds mapped over the surface. And these are the speeds such that if you launch a particle perpendicular to the surface at a speed at or greater than this, it will immediately depart on a hyperbolic orbit. So across Ryugu, we see these speeds range from 42 to 26 centimeters per second. On Bennu, they range from 12 to 22. This is very important for Bennu because those particles that we saw were actually being ejected at speeds in this range, and some of them up to meters per second. So actually them escaping from the body actually also has an influence on the rotation rate of this asteroid that we're studying right now. So sort of to summarize things, we can make some comparisons and conclusions between these two asteroids. Similarities really point to similar formation circumstances for bodies such as this, and we believe that these formed billions of years ago in the main belt. The shapes are remarkably similar. The density is equal to within the measurement uncertainty. There are some dissimilarities, and this really points to the randomization in the formation circumstances and of their subsequent evolution. The size is different by a factor of 2. Spin period currently different by a factor of about 1.8. The geophysical analysis of these bodies that was reported earlier this year concluded that Bennu has an apparently ancient surface in a highly symmetric shape. Surface is currently dynamically connected to the synchronous orbit structure as well, which randomizes any material lofted from the surface. Ryugu, we have reason to believe, has undergone some more extreme geophysical activity in the past because we, in fact, believe it was rapidly rotating in the past. And there's a APJ Letters paper that goes through that in detail. And its surface is currently dynamically separated from the synchronous orbit structure. Now, the important thing to note is that Bennu was rotating at the Ryugu rate quite recently. We can say this because we've actually been able to measure the change in spin rate of Bennu, and we see that it is now currently accelerating at a rate such that it will double in about 1.5 million years, which is relatively short for these bodies. That means less than this time in the past, Bennu was actually spinning at the Ryugu rate, and from a geophysical perspective, we probably had a very similar structure of motion on the surface and around the body. So with that, thank you for your attention. I'd be happy to answer some questions, go into things in a little more detail, and I'll leave this figure up, and you can try to cross your eyes and make that big boulder pop out at you. So, thank you. Okay.
Thank you.